Hi everybody, I think we're on notes number 33 today, and this is going to be kind of a treat because I think this is going to be a relatively short lesson. Maybe I shouldn't make that proclamation until it actually happens, but there's not a lot to cover in this one. This is from section 6.5, and we're going to look at the graphs of square root functions and cube root functions. And so the way we're going to start is let's think about what the graph of y equals x squared looks like, but just for x greater than or equal to 0. So let's see, I'm going to make a little graph grid here. Sorry, my lines aren't super duper straight. So we know it would go through 0, 0, 1, 1. I should make a scale. We should always have our scale shown. And then 2, 4, etc. Just drawing half of the parabola. So now what we want to do is graph y equals the square root of x on the same coordinate system. And perhaps you've never drawn a square root function before. Whenever we are encountering one that we've never drawn before, we typically like to plot some points. Now you might remember there was a lesson just recently where I did have a square root graph involved. It was one that I had originally done for a pre-calculus class, and so they had already learned that. So you might have kind of an idea already of what it looks like. If x is 0, the square root of 0 is 0, so we get 0 for y. Now I'm not going to just use any old x values, I'm going to strategically pick them. If x is 1, the square root of 1 is 1. And if x is 4, the square root of 4 is 2. And I'm not going to choose any negative x values because the square root of a negative is non-real, and when we're graphing on the xy coordinate system, we're only talking about real values of x and y. Okay, so I'm supposed to be graphing this on the same coordinate system. I'm going to use red for this one. So we have 0, 0, we have 1, 1, and we have 4, 2. And then we're going to have other points, of course, and we want to connect them with a smooth curve. And it's not going to go into quadrant 2 or 3 at all because it ends at the point 0, 0. Now, my curves that I drew look pretty close together down here in this part, but there's actually a little gap in between. So if you were to kind of zoom in on it, you would see this, and you would see this. Okay, there's a little gap in between. And one of the things you get to learn how to do when you get to calculus is how to find the area of a shape like that. A shape that's bounded by a curve above and a curve below. So that's something to look forward to. I think that's kind of a fun thing to do. So moving on, you can tell that these are inverses because they're reflections across the line y equals x. We could put that line in place here. They intersect on the line y equals x. And if you think about inverse operations, squaring and square rooting are inverse operations. So it makes sense that these graphs are inverses. The domain of y equals square root x and the range of y equals square root x. Okay, we can see from what we drew and from the process of finding points to plot that the x values have to be greater than or equal to 0. So that would be the domain. The other way to write that, if you write it using interval notation, is to start at 0 with a square bracket and then go to infinity. The range is also greater than or equal to 0, but we would say y is greater than or equal to 0, and it would look the same if we used interval notation, 0 to infinity with a square bracket on the 0. So if you have kind of a catalog in your brain of some of what the basic functions look like, so if I were to say, what does y equals x look like? You could visualize it. What does y equals x squared look like? You could visualize it. Well, the hope is that now you could add to that collection what the graph of y equals square root x looks like. Now let's do the same kind of thing for y equals x cubed. So we studied cubic functions in the last chapter. And if we want to plot a few points here, we could plot 0, 0, 1, 1, negative 1, negative 1, 2, 8, negative 2, negative 8. Kind of didn't give myself enough room for that. Whoa, Let's try that again. Well, I'm just going to leave it like that. Okay. And then what we want to do next is graph its inverse, which is y equals the cube root of x. So the cube root function or the cube root operation would be the inverse operation of cubing. So then we know for inverses we're going to switch x and y. So instead of the point 0, 0, switch x and y and you get the point 0, 0. Instead of the point 1, 1, switch x and y and you get the point 1, 1. Instead of the point 2, 8, switch x and y and you get the point 8, 2. We would have -1, -1, and we would have -8, -2. Okay, so if we go ahead and connect those points, once again, it's hard to tell, but there is a little gap in those little regions between 0, 0 and 1, 1, and between 0, 0 and -1, -1. So y equals the cube root of x is the red one. So it'd be nice in that catalog in your brain where you have visuals of basic functions if you had y equals x cubed and y equals cube root of x as well. And then let's go over the domain and range. Since you can cube root and cube, since you can cube root negative numbers and you get a negative, and you can cube root positive numbers and you get a positive, you can cube root any real number. So the domain of y equals x, the domain of y equals the cube root of x is all real numbers, as is the range. You can tell from the graph it's going to go infinitely high, it's going to go infinitely low. There's no gap in the middle. All right, for the second part of the lesson, we're going to use transformations to graph radical functions. So in other words, let's start with the parent function, y equals the square root of x, which has domain x is greater than or equal to 0 and range y is greater than or equal to 0, as we saw earlier. And let's transform it. So suppose we want to graph y equals 1/2 times the square root of x. What effect does the 1/2 have on the graph? Just like anything else that you're transforming, multiplying by 1/2 is a vertical shrink. So it's going to be 1/2 as tall as it originally was. So if I take some of the key points from my original graph, such as 0, 0, and I take half the height, it's still at 0, 0. If I take the point 1, 1, and I take half the height, now it's at 1, 1/2. If I take the point 4, 2, and half the height, now it's at 4, 1. And then looks like there's room for another one, so instead of 9, 3, we would have 9, 1.5. So this is still going to have the shape of a square root graph. It's hard to make it look like a curve, but it is a curve, it's not a line. It's just not as steep, half as tall. The domain is still x is greater than or equal to 0, and the range is still y is greater than or equal to 0. Those did not change. Okay, let's take this one. Y equals the square root of x minus 3. So we want to think about transformations and what effect does subtracting 3 from x inside the function have on the graph. Think about what we did with parabolas and absolute values and things like that. Subtracting 3 on the inside shifts the whole thing right 3. So if we take our original point 0, 0 and we shift it right 3, now we're at 3, 0. The point 1, 1 is now at 4, 1. The point 4, 2 is now at 7, 2, etc. So the domain has changed. Now the x values have to be greater than or equal to 3. The range is still y is greater than or equal to 0. There is an algebraic way to find the domain. You don't have to rely just on the graph. To find the domain, think about the radicand, which means the expression inside the radical sign. Inside the radical sign, you have to have a number that's greater than or equal to 0. So take the radicand and make it greater than or equal to 0, and then add 3 to both sides, and that gives you your domain. Okay, now this one is a little bit different because we have 3 minus x instead of x minus 3. So we didn't we didn't just add or subtract a number, we also multiplied the x by a negative, and we haven't really studied that in our transformations. That involves a horizontal reflection, or a reflection across the y-axis instead of the x-axis, but we haven't studied that before. So in that case, what I would do is I would make a little table of values. What if x was 3? 3 seems to be an important number because it would make the inside of the radical 0. So we would have the square root of 0, which is 0. What if x was 2? Then we would have the square root of 1, which is 1. What if x was, let's say negative 1? Then we would have the square root of 3 minus negative 1, which is the square root of 4, and that's 2. What if x was 4, or 3.1, or 3.01? Then we would have the square root of a negative, which is undefined. So it looks like the largest x can be is 3. So now we have a maximum value of x rather than a minimum value of x. So we have the 0.30, we have the 0.21, we have the -1.2. The curve is going in the opposite direction. See, I was telling you we would have a horizontal, or a reflection horizontally, kind of a y-axis reflection instead of an x-axis reflection. Okay, so for that, the domain is x is less than or equal to 3, and the range is still y is greater than or equal to 0. Now let's wrap it up with transformations of our cube root function. So make a quick sketch of the cube root function. And I think I'm gonna, well, I'll just go by ones. I was thinking about changing the scale there, but we'll just go by ones. So some of the key points here, we might not be able to make everything fit just perfectly on this amount of space. That's okay. Domain was all real numbers, and the range was all real numbers. So let's see how we're going to transform this. Okay, now it's going to be multiplied by 2. So what effect will multiplying by 2 have on the graph? Think about your transformations. That's going to be a vertical stretch, twice as tall. So if I don't change my scale, I'm not going to be able to fit in quite as many points. The 0.00 is still 0, 0, but 1, 1 is now 1, 2, twice as tall. -1, -1 is now -1, -2, twice as tall. And 2, 8 would be 2, 16, so way up there. So it is still a curve, it's not a line, it's just very steep. The domain and range are still all real numbers. And finally, the graph of y equals the cube root of x plus 1. Think about what adding 1 inside the function does to it. That's going to shift it to the left 1. So if we take our original graph and shift it left 1, oh boy, my lines. Okay, that's as good as it's going to get. The 0.00 is now at the point -1, 0. The 0.11 is now at the 0.01. The point -1, -1 is now -2, -1, etc. Something like that. But the domain and range are still all real numbers. It's pretty hard to change that. When you have all real numbers and you move something around, you still have all real numbers. Okay, so here's your assignment from section 6.5, and there's quite a bit of graphing. So the first few, when you graph, just go ahead and do them by hand as you saw me do in the lesson. When you get to 17 and 21, I think you should try graphing those on your graphing calculator, and choosing an appropriate viewing window is an important skill to practice. And then also when you get to 35, which is a word problem, it'll tell you in the directions to use a graphing calculator for that. Thanks, everybody.